Hey everyone, this will be a short tutorial on cutter selection and speeds and feeds for vertical milling machines, specifically CNC milling, but a lot of this would apply to manual machines as well. So today we're going to make this little part. It really doesn't matter, this doesn't do anything useful. I mean, it does kind of mate together sort of, but it's not important. The reason that I chose these two small pieces is because one has sort of an outside feature and one has sort of an inside feature. But when we get into the cutter selections and things, this stuff applies to almost any kind of part that has similar features. So let's start with this one. This is a very simple pocket. It's got a flat bottom and it's straight walls all the way from the bottom to the top. So this is about as basic as it gets for a milling machine task. So the first question is, how do you choose a cutter? Like if you're given this as the requirement, replicate this in aluminum using a milling machine, how do you get started? So there's all kinds of different cutters to choose from, and the thing to always keep in mind is that you want to use the largest diameter cutter that you can that will produce the correct geometry in here. So for example, if we used a really large diameter cutter like this isn't going to work because, I don't know if you can see that, the cutter diameter is actually bigger than the diameter, than the radius, that's at the edge of the pocket here. So if we tried to cut that with this cutter, you'd end up with too big of a radius there. And as it turns out, I made this part so that it would work well with a 3/8 inch diameter milling cutter, which is this size here. In more complex parts, you'll have inside corners and things that may be impossible to cut the proper radius. For example, if you have an inside square cut, that has a radius of 0 essentially. So that's impossible to cut with a milling machine in this configuration. And the best that you can do is use a small diameter cutter and get as close to 0 as you can. However, as you might imagine, using a really small diameter cutter is a pain in the butt because they break easily. So this is why you always hear machinists and mechanical engineers complaining about small internal radius cuts. If you want to make this little corner in here really sharp, that means you need to use a really small cutter, and then you have all these problems. So for today we have a pretty gentle, a pretty easy cut, and we can use a 3/8 diameter tool to get the job done. Second, you want to choose a cutter that's not unnecessarily long. So this feature is only about a 1/2 inch deep. The pocket's only a 1/2 inch deep, and it would be very, very stupid to use a cutter this long because all of this distance on the cutter can flex. Probably the single most important thing when setting up a machining operation is the total rigidity of your whole setup. So you might have a super powerful machine, with tons of steel and a really tight clamping setup. But if you put a long cutter in a tool holder like this and try to do the work like this, you're going to have a bad finish. And the reason is that the cutter itself is just going to wobble around too much. So I chose a 3/8 diameter end mill, and it's relatively short. So the cut is going to, there's not as, this is probably only about 1 inch long or a 3/4 inch long cutting area end mill. So we know the diameter and the length of the cutter that we're going to use to make this pocket. How do we choose the cutter material and coatings? You've probably heard a lot about, carbide tooling or high-speed steel tooling or stuff like that. And for home shops and hobbyists and prototype shops, high-speed steel tooling is fine. The main reason that production shops like carbide tooling is that you can go a lot faster. So if time is an issue for you, and it is for most job shops, you basically want to be able to run as quickly as you can and get that part out the door as soon as possible. But for hobbyists, the only downside is that you have to go a little bit slower with high-speed steel. And in aluminum, even that is not too much of an issue unless you've got one heck of a machine in your garage, but we'll talk about that later. Also, you've probably seen a lot of coatings on tools. So these gold-colored tools are titanium nitride coated, and it's always high-speed steel under here, although I've heard of carbide tools that are even coated now. And the coating is supposed to increase the life of the cutter. The idea is that the titanium nitride coating is harder than the high-speed steel material under it, and when you're cutting through something, it actually contacts the titanium nitride coating. However, in my experience, the coatings are kind of a waste of time. Nowadays, there's probably 5 or 6 different common coatings you can get. Titanium carbonitride, titanium aluminum nitride, aluminum titanium nitride, I don't know. And so there's tons and tons of coatings, but for cutting aluminum and plastics, you generally do not want a coating. I think zirconium nitride is considered okay for aluminum, but you generally just want a really sharp tool for soft things like aluminum and plastic. So if that's mostly what you're going to be milling, high-speed steel uncoated is perfectly fine. As you can see, most of my tooling is just high-speed steel uncoated. Okay, so now we know to machine this pocket feature, we're going to use an uncoated high-speed steel tool, and it's going to be only as long as necessary, and the diameter is small enough to make these features come out correctly. I should add that the high-speed steel tooling is cheaper than the carbide, which is of course why you'd want to use it. Otherwise, if money's no object, sure, use carbide, but there's probably some reasons why you wouldn't anyway. Carbide is more brittle. So if your setup is a little wobbly, carbide tooling is more likely to chip off. But anyway, that's kind of another story, so we'll talk about that later. So we've got the cutter set, the cutter chosen, and set up like this. Now we get to figure out how fast to spin this, and how quickly to push it through the work, and also how deep it should plunge into the work for every pass. And those are sort of the main cutting parameters that you'll be putting into a CAM, a computer-aided manufacturing software, or if you're programming this manually in G-code, what you'd actually be entering directly. So since we have the cutter material selected, it's uncoated high-speed steel, and we have the stock material chosen, it's a given in this equation, it's just aluminum 6061, we can figure out how fast we want to spin the cutter in the mill, because the spindle speed depends only on the material of the cutter and the material of the work. You'd want to vary it a little bit depending if you're having like a vibration or a clamping issue, but generally it's just a material property. And the way that we figure this out is actually empirically, and you can look it up on a speeds and feeds chart. The thing that actually determines what this number is the amount of pressure developed right at the cutting edge. So if imagine you're holding a knife and you're going to push the knife through metal. The tip of the knife is the only thing that's actually doing the cutting. The rest of the knife is there just to support the edge. And the edge is so small, I mean it's so fine, that the pressure and temperature right at that cutting edge is extremely high. I mean it's high, and worse than that, you can't really use coolant to cool it down. So everything that we're talking about here is not dependent on cooling or how much flood cooling or mist cooling or whatever. The cutting speed, the spindle speed, is limited by the material selection itself. So if you take a high-speed cutter and you start going too fast, that's basically like pushing a knife so hard through your material that the edge is going to fall apart because it's experiencing too much temperature and pressure. So one thing we can do is use tungsten carbide tooling, which is actually a composite. It's particles of tungsten carbide bound together in a matrix, and very often the matrix is cobalt metal. So the tungsten carbide particles are extremely hard, but the matrix cobalt is relatively softer. So there's all kinds of different formulations. You can have different particle sizes of tungsten carbide and different ratios of matrix to particle and all that sort of stuff. And that's why some manufacturers are better at making carbide tooling than others. In any case, it's pretty interesting to notice that the limiting thing in all machining operations is typically the material of the tool. We can always build a bigger milling machine that's got a more powerful motor, but the limiting factor is the tool itself. It doesn't really pay to make a machine more and more and more powerful because we're actually limited sort of by the physics of the material properties of the tooling. So we've got our high-speed steel tool here, and we consult the chart. This is for high-speed steel in non-ferrous materials, so aluminum. And down here it says aluminum alloys, 6061. And then for high-speed steel it says 450 to 650 SFM. That's surface feet per minute. This is a pretty horrible set of units here, but I've noticed even like shops that deal in metric units still use SFM, surface feet per minute to describe cutting parameters. In any case, what that means is between 450 and 650 is a good range for high-speed steel cutters, for that moving edge is going through the aluminum at about 500 feet per minute. So since this is a rotating cutter, what we have to do is convert that surface feet per minute, which is a linear speed, into a rotational speed. So the formula is RPM equals surface feet per minute times 12 to get inches per minute, divided by pi times the tool diameter to get RPM. So we're dividing by the circumference of the tool, and then that all comes out. The diameter is in inches. So for our example here, we've got, a lot of times, sometimes machinists will approximate this by RPM equals SFM times 4 over the tool diameter, since pi is close to 3. And the ranges that we're talking about are pretty big. I mean, this isn't an exact science. The reason that all these numbers are ranges is because your alloy might be slightly different, your tool might be slightly dull, the moon might be in the wrong phase. I mean, there's kind of a lot of different things that go into machining, and I'd say machining is about 80% science and 20% art, or maybe even less, and so there's a lot of things that go into it that are not hard and fast. So this comes out to be 5,095 RPM, which is actually beyond the top speed of my milling machine. So we're going to say that the RPM is going to be 3,800, which is a good comfortable speed for my machine. It's okay to go slower. What this is telling you is the maximum surface feet per minute. We can always turn the tool more slowly and then adjust the other cutting parameters to match, but you can't go faster than this without breaking down the edge of the tool prematurely. This is sort of a speed limit on how fast you can spin the tool in that material. If this were plastic, we could go much faster, because plastic, it doesn't present the same amount of cutting force that aluminum does. Okay, so now we know the cutter diameter, the material, this thing, the speed. Next we get to figure out how fast we actually want to push the cutter through the material. So we've got this spinning cutter here, and it's engaged into the stock, and we're going to push it in a linear direction through the material. We go back to our chart here, and it says for a tool diameter of 3/8 of an inch, if we're going to cut a slot, meaning that the cutter is completely surrounded by the stock material and we're going to be moving in a straight line. So generally, if you're going to be making a pocket, there's going to be some slotting going on, because you're starting off with a flat surface and you've got to push the cutter down into it and then start moving. There's more advanced tool paths that sort of make this easier, but for standard operations and for doing this on a manual mill for sure, you're going to be slot cutting. So this says for a slot, 3/8 inch tool diameter in aluminum, the chip load, which is a new term, is 3.8 thousandths of an inch. So we'll put that down. The chip load describes how much material is removed for every tooth on the cutter as it's going through the material. So if this thing's spinning and it's being pushed through the material, every time the cutter tooth comes around, it cuts away some of the material. And this is 3.8 thousandths of an inch. That's how thick the chip is. That's how much this thing advances for every tooth. And that number is determined by the tool manufacturer. I mean, in theory, you could go super fast. I mean, you could go incredibly fast, but what limits you is that the tool eventually breaks. So if you try to go too fast in the linear direction, sort of regardless of how quick you're spinning the tool, eventually you'll put enough force on it where it will snap off, or it will just dull, One thing that might seem a little counterintuitive is that you actually shouldn't go slower than this. In the case of determining the RPM that we want to spin the cutter, that's kind of a maximum, and we can always go more slowly if we want. But in the case of the chip load, you generally don't want to go too far below the manufacturer's recommendation. And this seems kind of strange, but what will happen is if you're not taking a big enough chip, like if this cutter is moving along and you're just sort of rubbing the surface, like you're not digging into it enough to actually cut off a good chunk of metal, what will happen is the material will try to burnish the edge. So instead of slicing off a piece, the edge of the material won't get cut. It'll actually just kind of rub along the front surface of the cutter. And what that does is it just dulls your cutter. And you'd be surprised how quickly you can dull a cutter by not pushing it hard enough. And again, it seems weird, like if you're having a vibration issue or the work isn't clamped down well enough, your instinct is to back off on the feed rate, which might help the vibration issue, but it will also cause a lot of premature cutter wear. So try to stick to this, and we'll talk about ways of reducing vibration without wimping out on the chip load. So some modern CAM softwares can take the chip load and just calculate all this stuff automatically for you, but I'll show you how to do it for the old-fashioned way if your CAM software won't. Okay, and the formula is the feed rate is the speed in RPM times the chip load times the number of cutters, or the number of edges on your cutter. So this is a 2-flute end mill, so it has 2 cutting edges. And we come up with 28.9 inches per minute. I should say, when we were choosing cutters, how do you choose how many flutes you have? So for example, this is a 4-flute end mill, and this is a 2-flute end mill. When you're cutting slots, it's generally a good idea to go with a 2-flute, and the reason is that all those chips that you're creating down in the slot have an easier time getting out if you use a 2-flute cutter, because there's just less volume of cutters kind of in the way. The downside is that you can't go as fast. So you can see from this formula, just by adding another set of flutes to the cutter, you can go twice as fast in feed rate. So the trade-off is, I mean, it depends sort of on your part geometry. If you're doing like a deep pocket, and this is a relatively good aspect ratio pocket, you really want to have some chip clearance to get those chips out, as we'll see later. Also, another thing to be aware of is some cutters cannot go straight down into material. So this one has cutting edges that go all the way to the center, and this one does as well. But some cutters, like this one, obviously you can't plunge that down into work because there's nothing there in the middle. So this cutter can't go straight down. It actually has to approach from the side, either at an angle or in a helix, or maybe it doesn't even cut in the middle at all. Okay, so we've got the cutter speed, 3,800 RPM. We plugged that into this equation, and we got 28.9 inches per minute. So these are the speeds and feeds that you might have heard about. These are that define your cut. The last number to figure out is how deep to put the cutter down into the material. So this pocket is about a 1/2 inch deep. We could, if we wanted, just go all the way in one pass and cut it out. The problem with that is that the cutter might snap off. So imagine in the extreme, I mean, let's say you had a cutter like this, you really can't put all that cutter down into material at once and cut off, because it would just snap your cutter. So a good rule of thumb when you're doing a slot is to not plunge more than half the diameter of the cutter. So in this case, the cutter is 3/8 of an inch, or 0.375 of an inch. So it would be good not to plunge more than half of that per cut. So what we'll do is go in half, or 3/16 of an inch, and then let the chips clear basically, and then drop another 3/16 until you get down to the final depth. Now if we were to just do that over and over again, so we start off at 3/16 deep, do a cut, another 3/16 down, do another cut, and all the way to the bottom, what we'd have with are a bunch of stair steps on the wall of our cut there. Inevitably what will happen is the cutter will have some slight forces on it as it's pushing through the material, and those slight forces will make something deflect. Either the cutter itself is going to deflect, or the whole milling machine is going to move a small amount, and our surface finish is not going to be the greatest. So what we do for almost all machining operations, you would do roughing cuts first, and then a finishing cut to get a good finish and to bring it to final dimension. So what we'll do is do these 3/16 stair step cuts that purposefully cut this a little bit undersize, and then we'll come back and put the cutter all the way down to the bottom of the feature, and then cut it to the final dimension. And that last cut will only involve removing maybe 5 or 10 thousandths of an inch of material all the way around. So there'll be much less cutting load on the cutter, and there'll be less deflection, and you'll get a better finish and a more accurate, a more precise cut. So a word about coolant and cutting fluids. Generally, some materials just work a whole lot better with coolant than others. So aluminum definitely is a material that benefits from having coolant, either a mist coolant or a flood coolant. The problem with cutting aluminum is that it's just so soft and squishy that the chips aren't very good at blowing away and taking the heat with them. Instead, the chips will stick to your cutter or stick to the work itself and transfer all that heat back into the work and the cutter. And eventually you end up with sort of a global heating situation. This is different from the heating at the cutting edge that causes us to choose between high-speed steel and carbide. This global heating issue is sort of a macro scale thing, and the cutting edge is sort of a micro scale problem. If you don't have coolant of any kind, pretty much your only option is to turn down the cutting speed, and then you have to put the new RPM value back into the feed equation and step that down as well so that your chip load stays constant. And this will work pretty well. You actually can just keep turning it down until you catch up with whatever cooling you have. Even an air blast is better than nothing at all. Another thing to mention is the direction that we're going to push the cutter if it's not cutting a slot. So let's say the cutter, this represents the cutter like this, on the edge of a piece of material. If the cutter is spinning clockwise when viewed from the top, we have the option of either making the cutter go this way around the object or the other way. So in other words, does the cutter drive into its rotation or drive away from it? When it's driving into the rotation, basically it's trying to chop the stuff that's coming toward it like this, that's called climb milling when the cutter is rotating like that. And on older mills, I mean like, very old, the first milling machines, this generally wouldn't work very well because there was so much free play in the mechanics of the mill that if you tried to push the cutter in that direction, the tooth would grab the material and yank the carriage forward on the mill, and then would bump the thing forward, and you'd end up with a gap here. And then as you keep turning the crank to feed more material, and it would grab another chunk and chatter quite badly. So they would tend to go the other direction, which for a long time, or still is, called conventional milling, where the cutter is going this way, but the work is going this way. So in this case, the chip starts off small as the cutter is going this way and gets thicker as it comes out the other side. This is conventional milling, and this is climb milling, where the chip starts off thick and becomes thin. Generally, all modern machine operations would use climb milling because you get slightly better surface finish. And free play on modern machines isn't really an issue because they all use ball screws now. Here's a question that comes up fairly often. This chart is very helpful, but it only goes down to a tool diameter of 1/4 inch. So what happens if you're using like a tiny little end mill like this? How do you figure out what the chip load is and everything? A good rule of thumb is to divide the diameter of the cutter by 150 to get a conservative chip load. For the other side of this project, there isn't really an internal feature, so what should our cutter diameter be? The answer is that you should use the biggest diameter that you comfortably can. So, generally getting larger than 3/4 of an inch is pretty uncommon for, smallish machines, especially ones that you might have in your garage. A 1/2 inch is a good size, at least for the kind of mill that I have, which is an old Bridgeport R2E3. And a 1/2 inch in this case is enough to clean this off in one shot. So, this piece started off as a rectangular prism, and we can come in here like this and basically in one pass get rid of all the material there. You might have heard the phrase high-speed machining thrown around a bit. I think the phrase is a lot like Web 2.0, where it means so many different things to different people that it's almost kind of meaningless at this point. There's a couple common threads though. I mean, obviously high speed, so you're spinning the tool a lot faster than you would in conventional machining. So for example, if you're using carbide tooling, here's the chart for solid carbide in non-ferrous materials. Under SFM, they say 800 to max, which basically means go as fast as your machine can handle. So if you're using carbide tooling especially, and your machine has a top speed of 10,000 RPM, go for it. Spin the thing as fast as you absolutely can, use lots of cooling, and basically just go for it. people realize that there's no reason to hold back, especially if the tooling is cheaper than your time. Who cares if it, has 75% life if you're going, 300% faster or more. Another technique that's common in high-speed machining is if you did want to clear away a lot of material, if you keep doing these small cuts, like let's say we were going to do this, clearing this away with a tool like this, we could take a little step, 20% of the depth and cut around, and then another step 20% down and cut around and all the way down to the bottom. The problem with that is, think about what happens to the cutter. You're repeatedly only using the bottom 10% of your cutter. So as you're using just that teeny little bit, the upper 90 or 80% of your cutter never actually sees metal at all until the finishing cut. So obviously that's wasteful. So high-speed machining says that you should use a very deep plunge, but don't go too far in the width of your cut. So this doesn't really apply to slotting because you don't really have much choice. But if you're coming in from the outside, you can choose how far in from the outside of the material you want, how big of a bite you want to take from the side. So a high-speed machinist would tend to try to use as much of the cutter depth as you can, and then just take as much off laterally as your machine can handle. And when I say machine can handle, I mean the fixture mostly. So if you have a very rigid setup and your machine is powerful enough, you can really remove material very quickly using this technique, hence the high speed. Other people will say, no, high-speed machining just refers to any spindle over 10,000 RPM or whatever, but it means a lot of different things. So I guess I'll end by saying that rigidity is really by far the most important thing in any machining operation. The coating of your bit or the exact number of flutes or this or that are all totally not important compared to how rigid your setup is. You always want to use the shortest cutter possible, the largest diameter possible, and always have your work clamped as securely as possible. Anything that extends out from the vise or makes it a longer path is going to be damaging to you. And if you're choosing milling machines, it's far worthwhile to get the most rigid machine you can. Even if it's, I would almost say it would be better to have a rigid manual machine than a flimsy CNC, but it kind of depends on what sort of materials you're cutting. You might think, oh, well, if I'm cutting small things, then rigidity doesn't matter as much, but you might be wrong. And the reason is that if you're using tiny little end mills like this, if your machine flexes a small amount, the cutter is going to break. So, if you're using a 1/4 inch cutter or bigger, you're going to have a little bit more flexibility in terms of how much your machine can flex, hardy-har. But if you're using this little guy, you basically get no second chances. So if you're cutting even in aluminum or something, and your machine is wobbling a little bit, it will eventually ruin the cutter. Okay, well, I hope that was at least somewhat helpful. I know it was kind of a brain dump and maybe not the most structured thing ever, but let me know if you guys have more questions about that, and maybe I'll do another more directed lesson if there's one topic in particular that seems useful. Okay, see you next time. Bye.